Something about the AEP for channels and superadditivity properties of measured relative entropies.
Okay, thanks for the kind introduction. So this talk is about, it's called quantum asymptotic equipartition. I guess this is a very foundational mathematical tools that is widely used in quantum information theory. And in this work, we give a extension or generalization of these tools. And we also show a few applications of these new properties. So this is a joint work with Hamza Fazi and Omar Fazi, and Omar is here in the audience. And these are the references on archive. Okay. So to start with, let's review what is asymptotic equipartition, right? So in the classical case, you can simply think of it as a form of law of large numbers in information theory. So basically, if you have a sequence of random variables, id random variables xi, then the joint probability distribution will converge to 0 exponentially fast at the rate given by the Shannon entropy. So this is basically the AEP, the most plain form. It is also called Shannon theorem. Okay, so this directly gives rise to the notion of typical set or non-typical set. So imagine that if you are working with a bit string of length n, a binary bit string of length n, then this will be a set of exponential large size. And then in this set, there's a small portion of this set which is called typical set, denoted in the red part. So the size of this set is very small, but it occupies almost all of the weight in this set. And more importantly, each element in the typical set has almost the same probability. So this is why it's called equipartition. Okay, so this technique has been widely used in information theory, such as data compression, channel coding, or cryptography tasks. So there's a more generic form to present AEP in these equations. So this is more, it is very nice that you can represent everything in one equations. So basically, you have two probability distributions. And usually for the second argument, we do not require the normalization condition, so it can be general non-negative function. So here, on left-hand side, you can choose a divergence of your interest. And epsilon is a smoothing parameter. And you take n copies of it, and you ask whether the left-hand side converge as n goes to infinity, and where it converges to. And usually, this quantity will converge to the KL divergence or relative entropy in the classical case. Okay. So why we say this is a more generic form? Because if you think of, if you take the divergence on the left-hand side as mean entropy and max entropy, and you take Q as a constant function, then this will reduce to the AEP that I've introduced in the previous slide. And also, it covers if you think of the divergence as the hypothesis testing relative entropy, this will recover the well-known Chernoff-Steins lemma in classical setting. So it's a very generic form to represent AEP. Okay, so with this kind of AEP, we can now generalize it to the quantum setting. Right? So we can follow the standard routine to leverage classical information theory to quantum. You simply replace the classical probability distributions with density operators. And again, the second argument usually do not require the normalization condition, so it can be a positive semi-definite operator in general. Okay, so here in the quantum setting, you have two quantum state or density operators. And again, on the left-hand side, you replace the classical divergence with quantum divergence of your interest. You still have the smoothing parameters. And you ask the same question. If we take n tensor copies of your quantum state, whether the left-hand side converge and where it converge to. Right? And usually in the quantum case, this will converge to the quantum relative entropy introduced by omega key. Okay, so this kind of AEP has been extensively studied in this community. In particular, here and Paz studied the case that the divergence on left-hand side is the hypothesis testing relative entropy. And later, Ogawa and Nagaoka show that, okay, the convergence on the left-hand side do not depend on the epsilon you choose. So you can remove the limitation in the outer layer, and this, the convergence still holds. So these two results together now referred to as the quantum states lemma. And of course, for the other, there are plenty of divergence that you can play with. And here I just list two. So Marco and Renato Renner studied the case of conditional entropy, and also later with Hayashi, they consider the max relative entropy. Okay, so there are plenty of entropies and special cases you can play with in this framework. And this lays the foundation of many quantum applications, right, in the community: quantum data compression, state merging, channel coding, everything. So I guess for most of the information tasks, if we want to extract what is the asymptotic rate or the optimal performance in your task, you have to more or less use this kind of AEP things. Okay, but it's but this formulation has a bit limitations for it, right? So in most of the literatures, they put the focus on the singleton case, which means on the left-hand side you study the case that you have just one quantum state, rho tensor n, and this quantum state has to impose as the IID structure. Okay, but this is a little bit limited. So we can consider a more general question that fits better to this workshop, right? What about beyond the IID case? So what if the system between each copies have correlations? It is not necessarily in the IID structure, and also sometimes we don't have precise characterization of the quantum systems that we manipulate. So we only have partial information of it. So the status of the quantum systems are described by a set of quantum states, not a single quantum state. Right? So in this case, people have studied this more general framework in the classical case, and they have right. So they have also shown some of the practical applications, such as speech recognition, radar target detection, some of those practical things. Okay. Anyway, so I guess this is not important in this workshop. So we focus on mathematical perspectives. Okay. I'm mentioning this because okay, this is not a completely mathematical abstract of AEP, but it indeed have some of the motivations. Okay. So this motivates us to explore what happens in the quantum, right? So can we have a more general quantum AEP that goes beyond the IID case? So now, more specifically, we consider the problem like this. So if you are given two sets of quantum states, AN and BN, and you compare the divergence between these two, and so if you think of a divergence between quantum states as sort of distance between these 2 points, then the divergence between these two sets can be naturally defined as a minimum distance between the sets. You pick any quantum state rho in A and sigma in B, and you compute divergence, and then you implement over all the possibility in the set. Okay, so basically this is the distance between these two sets. And now you can ask the same question, whether the left-hand side converges when n goes too large, and where it converges to. Okay, so this will be a very general framework that I believe contains all of the existing literatures. In particular, in the generalized quantum states lemma, it is case that the first set, okay, AN is still a singleton IID quantum state, and B is a general set. And in the Shannon setting, you reverse these two properties. So the first argument is still a set of quantum states, but the second argument is an IID singleton case. So the question we ask here is very general. Okay, so the answer is like this. This is the main result we have. So basically, we say the left-hand side indeed converge, and it converges to the relative entropy between these two sets. Right? So this is the most natural things that we can expect. So the right-hand side is given by the quantum relative entropy between the sets, but in general, this quantity is not additive, so we take the regularization of it. Okay, and this will be a very general result in the following sense. The first one is that the divergence we prove is hypothesis relative entropy and Dmax. So these are two extreme cases in a bunch of divergences. So anything that lies between or equivalent to them, you will get same asymptotic rate. And in terms of the set that we are working with is that, okay, so in order to make the left-hand side converge, you have to impose a few structural assumptions on the set that you are working with. Okay, so here, most precisely, we require 4 assumptions on the set. The first one, okay, the first 3 are very natural and widely used in the previous works. The set should be convex compact, so it's a well-behaved optimization problem. And also, when if you think of the nth levels, the set has to be permutation invariant, and also it should be closed on the tensor product. Okay, so these 3 are widely used in the literatures. And the slight difference is that here we require the assumption 4, means that if we look at the polar set of the set you are working with, then we also require that the polar set is also closed on the tensor product. On the right-hand side, this is the definition of polar set. It intuitively give you the description of the dual picture of your original set. Okay, so these are technical assumptions, but we do find many cases of interest that satisfy these assumptions. Of course, in the case of singleton, you can easily check they satisfy all the assumptions. And also the conditional state means that you have identity operator on the first system, then you tensor all the possible density operators on the second system. So this will be related to the conditional entropy in many studies. And also in the channel image, you fix the channel and you study the image of the channel. So this set will also satisfy the conditions. So I will introduce the application in adversarial channel discrimination later. Okay, and also the rest of the cases. There's one extension set, right? So this will be the set that related to the Woolman theorem that we work with. Okay, and a bunch of sets that is used for in quantum resource theory. Okay, and more importantly, right? So 8.4 may look a bit technical and yeah, make some people uncomfortable to accept this. But we have to say that without this assumption, the AEP will not hold. So there's a few counterexamples in these references. I guess the counterexample is even given in the Shannon settings. So in order to make this general framework converge and well-behaved, you have to impose additional assumptions. Okay. So the polar assumption is the one that we use. Okay. And here we would like to emphasize more on this AEP is that, okay, I gave a 5-star here. This is really the thing that we want to emphasize, that really discriminates the AEP that we have to the other cases. Is that the right-hand side is given by a regularized quantity, right? So in order to get the optimal rate, you have to compute the quantity for extremely large n. But in our cases, the regularized quantity is well behaved, so it's explicitly lower and upper bound, and we can control the gap between lower and upper bounds very well, so that we have a efficient algorithm that help you to estimate the asymptotic quantity. Okay, so the message here is that indeed the optimal rate is given by a regularized quantity, but we can still efficiently compute it. This is the good thing in our framework. Okay, so we write the computational efficiency aspect of this thing in a separate archive paper. Okay, and also in the full paper we have slightly stronger results than the AP that I present in the box. So essentially, we have a finite n estimate of the quantity that we estimate. Okay, so this is up to the second order terms. So if you divide it by n on each side of this equation, then you recover the result in the box, right? So so this will be a stronger result. And also, if you look at the finite n estimate, you will see that the leading order term is given by the regularized quantity, but we can still give a finite n estimate. So we have a sense of control to the convergence that of the AEP. So yeah, so this is a very real cases in quantum information theory, maybe the first one I know. And also, the limitation here, the convergence of the left-hand side does not depend on epsilon, so it means that it has the strong converse property. And of course, the second order term we show here is not the usual case of square root of n, so there's still potential improvements that can be done here. Okay. Okay, good. So how we made this, right? So this is the technical tool that we use. Essentially, we want to approach the target quantity d from both sides. From the upper bound side, we use the sandwich linear divergence, and from lower bound side, we use the major relative entropy. So once we impose the technical assumptions, in particular, if the set is closed on the tensor product, then you can easily argue that the sandwich divergence between the set will be sub-additive. So you will converge to the thing that you have from above. And if we impose the closeness of the polar set, then you can argue that the major relative entropy between the set is super additive. So it will converge to the thing from below. Okay, this is the idea. Okay, and here are a few more words on the polar assumptions. So many years ago, we know that there's a variational formula, very useful representation for major relative entropy by Mario, Omar, and Marco. I guess all of them are here. And in this work, because we have studied the divergence between two sets, now we have an analog variational formula for that. And the objective function here, HA, is the support function of X on set A. Okay, so simply you take the inner products of X with all the possible operators in the set A. So this is the support function. So because we want impose that the major relative entropy is super additive, so it converges to the thing that we have. So it naturally shows up the polar set assumptions. Okay, this is where the polar assumption comes from. Okay, so the polar assumption, the closeness of the polar assumption can be shown is equivalent to impose the sub-additivity of the support function. Okay, by simple arguments. And later, actually last week, Milan told me that, okay, maybe we have a slightly better understanding what this polar assumption is. So if you look at the definition of the support function, right, so it looks very similar to the type 2 error probability, the worst case type 2 error probability for distinguished set. So if you look at this quantity in this perspective, the polar assumption can be equivalent to the sub-additivity of the worst case type 2 error probability. Okay, this gives you a slightly more operational understanding of what it is. Okay, but yeah, again, so maybe there's a better understanding of this. Okay, thanks Milan for letting me know. Okay, let's recap what we have done here. So we know that the AEP can be written as a generic form in these equations, and this helps us to do a quantum extension of the AEP. And now in this work, we extend this further to discriminate between two sets of quantum state. And we show the AEP in this general framework under a few assumptions. Okay, so for now, it's completely mathematical reasoning. And now I will show you where we can use it. Okay, So here, of course, it's closely related to hypothesis testing between two sets of quantum states, and we also show application, a new variant of quantum channel discrimination that is closely related to this generalized AEP, and also relative entropy accumulation theorem that is very important in quantum cryptography tasks, and of course, the last one is resource theory. Okay, I'll introduce them one by one. The first application is hypothesis testing, right? So here you have two sets of quantum states, A(n) and Bn, and the tester can draw samples from the set and perform measurement to make a guess where this sample comes from. So as the standard hypothesis testing, you have two kind of mistakes. Type 1 error, say the sample comes from A(n), but you classify it as Bn. And type 2 error, say it actually comes from Bn, but you classify it as An. So you can define the two worst case error probability as well. Okay. So the quantity of interest in here is that, at least in the asymmetric case, we want to control the type 1 error probability within a constant Schwarzschild code epsilon. And with this constraint, we want to minimize or optimize the type 2 error probability that we have. Okay, so the optimal type 2 error probability is defined as beta here. So the question here is how, what is the optimal behavior of this type 2 error probability? So this is the answer. So the type 2 error probability is still exponentially converged to 0 at the rate given by the relative entropy of these two sets. Okay, and this holds for any epsilon between 0 and 1. Okay, so you can understand this as a new generalized quantum state lemma. Yeah, we don't have a better name for it, so we just say it's still a generalized quantum state lemma. Okay, of course it covers the classical case easily, and also cover the plain form of quantum state lemma that you simply choose the set you consider as a singleton IID case. Okay, and it can be related to the more well-known generalized state lemma by Renato and Planio. This is related to the first two talks in this workshop by Hayata and Ludovico. Okay, and now I will explain the relations or differences between these two generalized quantum state lemmas. Okay, so the generalized quantum state lemma by Renato and Planio started the case that the first set is still IID case, but the second one is a general convex set. Okay, this was proposed by Renato and Planio 15 years ago, and everyone knows that there's a gap there. But luckily, right, so very luckily we have at least two solutions to save the results. So the story has been introduced by Hayata on Monday, so I will skip this part. Okay, so I guess most of people would be interested or curious what is the difference of our generalized state lemma with theirs. So I do a comparison here. So of this, this first equation is the state lemma by Brandon Planio, and the second one is ours. Okay, so of this state lemma has to impose some of the structural assumption on the set that we are working with. So I summarize in this table. In particular, Ludovico let me make use of these 5 assumptions that are originally proposed by Brandon Planio, and Hayashi and Yamasaki's proof can recover the same result but use fewer assumptions. And also here, the red part is our work in this talk, right? So we have an analog of quantum state lemma, but use slightly different assumptions. In particular, we use the first 3 assumptions by Brandon Planio, but we have to add additional assumption on the polar set. Okay, so this is the summary of this these things. Okay, so in summary, so our new generalized state lemma is not directly comparable to the previous one that most people know. It is weaker in the sense that we have the polar assumption. Okay, this is a bit restrictive. In particular, for the set of separable states, we know that it does not satisfy this assumption. So we cannot recover Renato Planio's result. But it is stronger, at least in 2 senses. The first one is that we allow composite hypothesis in first argument. And more importantly, the optimal rate on the right-hand side can be efficiently computed. So the convergence of our Slay's lemma can be efficiently controlled or well behaved. So this addresses the open problem in 2 of the works. They're trying to explore whether there exists a more a generalized dense lemma with efficient computational efficiency. Okay. Good. So yeah, so Brenner-Planius generalized dense lemma has a lot of implications or applications, or it attracts a lot of people to care about because it has this application, right? It shows the reversibility of the manipulation of quantum entanglement, or AKA called second law of quantum entanglement. So because we have this a new generalized quantum dense lemma, so we can have an analog result like this. So so the plain form of reversibility is that you transform n copies of rho to m copies of sigma, and later you can transform it back without any loops. Okay, so it's a reversible framework. And here we can work with 2 black boxes. Okay, AN and BN. You can also define a similar transformation task to transform black box AN to another black box BN, and you can also transform back. So we can show that the optimal transformation rate is still given by the fraction of this relative entropy between the set. Okay, it's an analog result. So this black box transformation can be related to Kaito's talk on Monday. Okay, this is a side remark. As for the second application, we define a new variant of quantum channel discriminations. So in this task, okay, so we have an untrusted black box or quantum devices that generate quantum states upon request. So imagine that the device has a bottom, and you click the bottom, it generates a quantum state from the box. Okay, so the difficult part in this scenario is that this is an adversarial setting. So the adversary controls the box. So it can also control the environmental system of the channel, and it has also potential internal memory that correlates things. So the adversary will play against the tester to mislead the tester to correctly classify the channel inside the box. Okay, so the question is here how efficiently, right, the tester can distinguish between the good case or the bad case while playing against this adversary. So the classical case has been studied by Brando and Amharo in this paper. We give a sort of quantum generalization of this task. Okay, so if you look more closely at the box that I have here, so everything inside of the red box is controlled by the adversarial, and everything in blue is accessed by the tester, right? So in the first round, okay, so the tester hit the bottom, the adversarial prepare a quantum state. He can do some preparation operation P and send the system A1 through the channel and return the output system B to the tester. Okay, so E1 is the environmental system of channel that inside the box. Okay, but the environmental system is controlled by the adversary, and the adversary may also have some internal memory R that he can use the information of the environmental system and internal memory for the next step, right? So if you hit the bottom again, it should generate another quantum state, but the adversary can prepare some intermediate update before generating quantum state. Okay, so because the tester only knows the bit systems, so he only has partial information of what he can control. He don't know what happens inside the box, right? So the information that the tester can access, we denote it as AN if the device behaves as N, and if the device behaves as M, then the information that the tester can access is BN. Okay, so this is the adaptive strategy by the adversary, and also there's a simpler strategy which is non-adaptive one. So the adversary can simply throw away the environmental system. Don't use it anymore, and do not do any update, the trivial update between each rounds of the protocol. Okay, so this is the very simple strategy by the adversarial, and we also denote the information that can be accessed by the tester as an prime and bn prime. Okay, so what is the optimal performance in this adversarial setting, right? How well the tester can play with against this adversarial. So the result is here. So no matter the optimal type 2 error probability, if the adversarial perform adaptive strategies or non-adaptive strategies, they converge at the same rate given by the relative entropy of these two quantum channels. Okay, so the last notion is a new type of channel divergence. We just write it as dinf. Okay, you have two quantum channels. You select two quantum test state, rho and sigma, and you compute the difference of the output state. Then you minimize all the possible choice. So this is kind of worst case channel divergence. Okay, of course we define the regularization of it. Okay. So we found that the optimal performance is exactly or precisely characterized by this kind of worst case channel divergence. And you can also see that, okay, the adaptive strategy performed by the adversarial will offer him or her no advantage at all, right? So in either cases, the performance are the same. So in some sense, this is a good news for the tester because the adversarial can perform very complicated strategies to play with the tester, but essentially they make no difference as the non-adaptive ones. Okay, so the technical tool we use to prove these results is new chain rule properties. It basically says, the first line basically says, if you have two quantum channel N and M, and you send two quantum states rho and sigma, then the divergence between these two output states can be lower bounded by the contribution from the state plus the contribution from the channel. Okay, this is kind of chain rule in the lower bound direction. And this chain rule holds for any alpha from 0 all the way to infinity. Okay, and then if you regularize the first line, you get sandwich. Right? But this works for alpha larger than 1/2. Okay. Okay, good. Now the third application that is closely related to the entropy accumulation theorem used in quantum cryptography. The entropy accumulation theorem says that if you have a sequence, you have an input state, then you apply a sequence of operations on the state. And what is the entropy in the final output state? So the entropy accumulation theorem states that the entropy or the conditional entropy of the output state is accumulated or contributed by the entropy from each of the individual steps. Okay, so it accumulates. The more applications you apply with, the larger the entropy will be. Okay, this is the statement. And then there's this question asked whether we can extend this conditional entropy form to more general relative entropy form, right? Because we know, yeah, so conditional entropy is a special case of relative entropy. So this was asked by a recent work by Omar, David, and Renato for DMAX. Okay. And here, if you still remember the channel discrimination task, and you will see that these two diagrams are actually very similar, right? So our new contribution is that, so actually the relative entropy task, relative entropy accumulation task can be understood as a special case of channel discrimination task. Okay, I will show you how to do the specification. So first of all, the first diagram is for relative entropy accumulation theorem. You apply a sequence of operations on the input state. You see how the entropy accumulates from the tester perspective. So first of all, you can write the Stein-Sprint dilation of each of the individual process, but then you can throw it away. So they're equivalent. This is trivial. Once this is done, you can take a special form of each of the operations and system in the adversarial channel discrimination setting. You'll see that it will exactly recover the entropy accumulation diagram. Okay, so this is not very straightforward when you look at this at first sight, but yeah, it spends like two or 3 minutes to specify this. Okay. Anyway, so I just want to say relative entropy accumulation theorem can be fit into the channel discrimination framework. Okay, so with these ideas, we can now make use of the proof techniques that we have for the channel discrimination task to get a entropy accumulation result here. Okay, so the resulting box is our answer, but we proved this for hypothesizing relative entropy. So you have two input states, rho and sigma. You apply a sequence of operations, Ni and Mi. Then you can evaluate the divergence between these two output states. So eventually, this divergence is lower bounded by the contribution of each of the individual operations that you apply. Okay. So with this result, we can recover the original entropy accumulation theorem with a slightly weaker second order term. Okay. But yes. So the idea here is that we have a new perspective to look at entropy accumulation theorem. It might provide you better results in the future works. Okay. Good. Okay. How much time I have?
Maybe 5 minutes.
Only 5 minutes? Okay,
maybe
good.
6, 7.
Good. Okay, that's enough. Because this application is not that important. So for many of the audience, okay, this is a resource theory application. Okay, our AAP have some technical assumptions, right? So especially the set of several states that most people interest do not fit into this framework. So the thing we can do is, okay, we do relaxation that make your theory fit into our framework. Okay. So the idea is that we really want to make use of the advantage of the fact that our asymptotic rate can be efficiently computed. Okay. So we apply this idea to a few resource theory tasks. It helps to give you some quantitative improvement of the optimal rate that we have. For example, in time, the task of intermittent cost or intermittent distillation or magic distillation. Okay. Maybe I can briefly introduce one. So the intermittent cost is the minimum number of Bell states that you require to prepare a quantum state, right? But this quantity is extremely hard to evaluate on the LCC. There's a lower bound given by the regularized PPT entanglement, okay? But PPT, again, we can show that it doesn't satisfy the polar assumption, so we can do relaxations, okay? For example, you just relax it to the range set. Okay, it will fit into our framework, and we can show that once it is done, you can show that the regularized relative entropy of rho with respect to this new set can be efficiently computed. Then it will, if you run it numerically, you'll see that there's a quantitative improvement against previous results. Okay. Yes, this is the numerical thing that we run. Okay, clearly it gives you improvements, and this. Okay, and there's a few other quantitative improvements in other tasks. Okay, resource theory tasks, resource theory of magic states distillation. You relax the set of stabilizer state to a set that is analog to the range set. Okay, then the relaxation will fit into our framework. Good. Okay, so this is a summary of the talk. So basically, we have a extension or generalization of the AAP that we are working with. We can show that it indeed converges to the thing that we expect under certain assumptions. And the technical tool that we use can be useful maybe in some of the future works. And yeah, because AAP really lies in the heart of information theory, so we expect that this new framework will have more applications in the future. And actually, there's a not on this one. Okay, there are a few of the works that already make use of the generalized AAP in their work. Okay. Okay, this will be the last slide. So okay, yeah, I've put out these advertisements everywhere. So I'm now working in the Chinese University of Hong Kong, Shenzhen. Okay. And now I'm looking for postdocs, PhD students. So you have interest in working with me, you talk to me in the workshop. So this is the picture from the university. It's based in Shenzen. Okay, so you have nice weather, very beautiful campus. Okay, and also Hu Air is there, right? So we have Masahito, and Masahito. Yes. So yeah, a lot of Masahito is there. He's so productive that he himself is a team. So in this sense, we have a large group. We have a large group there. Okay, and we will get better understanding of more information of these templates because next year beyond the ID we will organize this workshop there. And okay, so of course Masahito is the leader, and I and Xin Wang is also here. Yes, so the planned date is just so ISIT next year will be in Guangzhou. So we plan to arrange this beyond IIT 1 week before that, so people can combine these two trips together to attend these two events. Okay, and also on right hand side, this is a picture from Google Map. Okay, here this is Guangzhou. ISIT will be here, and next year beyond IIT will be in Shenzhen. Okay, so actually next month AQS will take place in Hong Kong. So this place are called Great Bay Area in China. So it's actually a very active place to doing information theory. And in Shenzhen, right, so you can see that QFP, beyond IIT, ITW all take place in Shenzhen. So it's a very international place to work on information theory. And also in China, now we have a very generous visa-free policy for travelers. So please join us next year, okay? Good, okay, so this is all I have for today, and thank you very much for your attention.
Okay, thank you, Kun. Questions? Okay, maybe.
A question on the assumptions like that you have for the generalized AEP.
Yes.
Would it also be possible that, for example, that you prove it if A4, like you have this equivalence for the support function inequality? Like if the support function inequality doesn't really hold exactly, but holds like only asymptotically with a small error?
Yeah, I think that would work the same as well. Yes.
Okay. Yeah. And another, like related to that, maybe also like according to the A3, maybe I would imagine I have sets that are permutation invariant.
Yes.
And if I take the tensor product a priori, it's not permutation invariant. So I could imagine that I modify A3 by saying not that the tensor product needs to be contained, but that an additional permutation needs to be contained. So it's a weaker assumption. And I wanted to know whether you think it would still be strong enough or not? Okay,
so it's very clear. So the assumption of A3 is to ensure that the sandwich one is sub-additive and converge from above. Once we have these things, I believe everything works. And also assumption 4 is a dual picture. Right? So once we have this, the major radical entropy will converge from below. So essentially, if you can ensure that they converge to the right thing with weaker assumption, I guess all the results will work in the same way.
Okay, last chance for one question. Okay, otherwise let's thank Kun.
Okay,
again,
thank you.
And we continue.